Here's some armchair cosmology for you. So, rays of light traveling from the sun hit us in parallel lines because we're so far away from the sun that anything that's less than directly aimed at the earth, any photon that's less than directly aimed at the earth, is going to ultimately not hit the earth. So, for all intents and purposes, the rays of light are parallel. Now, if something is closer to the earth, like the moon, say, the rays of light are still kind of more or less parallel, and so on and so forth. The closer the light source, or the reflected light source, is from the observer, the more the lines are going to be parallel, right? But once you get to a large enough scale, we're talking the amount of gravitons involved are far more substantial, then you'll find that the actual position of, if you assume the rays are straight, then you're not coming from the right position. If you think the rays are traveling in parallel lines, then that's not true. So a distant star, and say in the Cygnus constellation, or wherever, however many millions of light years away, or billions, or even but once you get to the point of the background, the cosmic background, microwave background, at that point, parallel lines simply do not exist. Where the whatever stats you're getting on that light that's hitting the sensor, from which you derive the shape of the microwave background, cosmic microwave background, however you derive that, it's not the actual positions of those aberrations in the background. That's not where they actually are. It's too far away at that point. You can't. So the further away an object in the cosmos, the greater the degree of inaccuracy when it comes to measuring it without taking into account intervening matter, and therefore the effects that it has on the isographs. Because even though on a nearby scale the sun's rays aren't bent by Mercury, say, I mean, if they were even that's negligible, they could be, it'd be so negligible, but the star's rays are bent by intervening mass. Therefore, isographs are what? Isographs don't provide for a Euclidean geometry, three-dimensional geometry. We already know this, to space. So, the hypothesis is that the universe is not expanding. It just appears to be expanding because the further away the light source, the more stretched the isographs along which those light rays travel to reach us. And that's what's stretching the wavelength out. Not they're receding from us, but just the fact that in order for the entire universe to be cogent and wrap in on itself, pi cannot apply at the largest scales. And to make up for that, the universe is stretched along isographs, which leads to redshift, and it's not the Doppler effect. So the cosmic microwave background is simply the residual effect. Not the residual effect, is the furthest you can see, because beyond that, the edge, if the universe, so the universe has some angular momentum It has to have some angular momentum. But what's the distance beyond which, if you calculate how fast the wheel is spinning versus the hub, that the tire is spinning versus the hub, well, as soon as the tire's going at the speed of light, well, you've reached the CMB at that point. So that's all it is. It's just there's a limit to how far you can see, because, and it's exactly equal to what that would be given the minimums and maximums that we know about. You would find that if the universe was a sphere and it was spinning at the smallest possible speed, that its surface, that the cosmic microwave background would be located at a distance where that surface would be spinning faster than the speed of light. Hence, we can't get information past. I mean, it's there, but then suddenly we have like this shell. And beyond that, there's no greater distance than that. So that's all it's shown us, that there's no greater distance beyond which we can see. But it's got to all be connected to itself. And the only way it can do that, considering pi, is for there to be redshift. It has nothing to do with the Doppler effect.